could you please explain?
Okay, see, you have understood up to this formula, no? This is the relationship between potential energy and internal conservative force, that delta U is negative of work done by internal conservative force, right? This statement is clear?
Yes, sir.
Okay, so work done by any force is F dot ds in integration.
Yes, sir.
Right? So what we mean by a one-dimensional system? The system is such that everything is, I mean, the motion of the body and the forces, everything in that system is along one particular axis, right?
Yes, sir.
So if we have a one-dimensional system where the motion is happening along the x-axis, then what we can say about the force? It will have only an x component.
Yes, sir.
And the displacement will also have only an x component. No?
Yeah.
So that vector relationship F dot ds will reduce to what? A simple component relation F's x component into dx.
Yes, sir.
But understood. So that's the idea. Whereas, for example, if this was a 2 or 3-dimensional system, then there would be more terms, right? Because the displacement would be dx I cap plus dy j cap plus dz k cap, like that.
Yes, sir.
Right? So that's how we have reduced this formula of the dot product into a simple product, because it is a one-dimensional situation. So because the force also has only an x component, the displacement also has only an x component. So the dot product F dot ds has become just F into dx. And of course, for du, we have minus F dx. Right? Okay, so this is the 1D relationship between force and internal conservative force and potential energy. Now let's look at an example problem. Okay. Okay, so this is a very direct type of question. Okay. Potential energy is given to you as a function of x. From this, we have to find the value of the internal conservative force as a function of position, or that means as a function of x again. Just try out this question, apply the same method as above. Okay, anybody worked out this question?
Yes, sir.
Yeah, so tell me the formula for force.
Or minus du by dx. Yeah, we can apply that directly, right?
Yes, that only has to be applied. Okay, so
Okay, no
potential
problem.
energy has been given to you here as some constant alpha divided by x. Okay. So it's a 1D system along the x-axis. So force will be negative of differentiation. Right, differentiation of 1 by x is minus 1 into x to the power minus 2. Okay, so hope this example is clear, people.
Yes, sir.
Sir, one thing, what did you write in the right side? D by dx of 1 upon x.
That is the formula of differentiation. No, beta?
Like,
Differentiation
oh, okay,
of
okay. I thought that
x
is the answer for it.
n.
No, man. Okay, yes, sir. Okay.
Okay, so we are just using that over here. Okay, so done with this. This is clear, no? Okay, now next thing we will understand is the concept of stable and unstable equilibrium position. Something versus stable or unstable equilibrium. For a one-dimensional system, with zero external force and zero non-conservative force. So what that means is basically the net force is the internal conservative force. So for that type of a one-dimensional system where external force and non-conservative forces are absent. Okay. So the net force acting on a particular body is the internal conservative force. So for this type of a system, the net force, which is the internal conservative force, is minus du by dx. So if we are to visualize, suppose you're looking at the graph of potential energy versus position, then from this graph, what information we can get about internal conservative force? It is negative of the slope. So the net force acting on a body is negative of the slope of u versus x graph. So for example, if the graph is like this, then at any point, select x1 over here, you can see the slope is positive. So that means the force is negative. So the direction of the force and by force we mean the net force now. Similarly, now suppose we have a point like this x2. At such a point we can see that the slope is negative, du by dx is negative. Okay, so that means the force is positive. Okay, now additionally you can see that if you look at this point, the slope here is 0. Or if you look at this point here, the slope is 0. So if these points are, let's say, x3 and x4 respectively, you can see that at these 2 points, so U has a local maxima and
local minima.
minimum, right, respectively. So that means du by dx is 0 at these points. So which means the force is 0. So the force is 0. It means that they are equilibrium points. Because that is the definition of equilibrium. That net force is 0. So first of all, from the graph of potential energy versus x, how we can identify any equilibrium points in such type of system. We can identify the points where there is either a local maxima or a local minima. In other words, the points where the slope is 0, those points are the equilibrium points. Okay, so first note down this much. Then we'll see further that we can classify the equilibrium points into 2 categories: stable equilibrium versus unstable equilibrium. So I'll explain also what stable versus unstable means. Okay, now let's look at stable versus unstable equilibrium. Now, one way to simply define which one is stable and which one is unstable is by looking at the potential energy graph. Okay. A stable equilibrium position is a point at which the potential energy has a local minima. Okay. But also in terms of force, let's understand what this means. Okay. Yeah, Rishit, I'll scroll up just a minute. Okay. So, as I was saying, one way to define the stable equilibrium position is the position where the graph has a local minima. But this also has a logic behind it, that why the local minima point is called the stable equilibrium point. Let's understand that. So as the name suggests, stable equilibrium means that when our system is in that particular point, obviously equilibrium means net force should be zero, but it also means that it has a tendency to come back to that point because it's stable at that point. Okay, so if we move the system away from that point also, it should have a tendency to come back to that point. So if this is our potential energy graph, okay, so you can see that suppose this point is x equal to a. So at this point, we have the local minima. So U has local minima at x equal to a. So that means two things, that du by dx at x equal to a is 0. So that means there is equilibrium. But it also means that what about du by dx at a point like this, slightly beyond this point? Okay, so if I'm now talking about point over here, where this is delta x beyond, okay, you can see that the slope here is positive. Okay, at this sort of point. So that means what about the force? The force is negative, because remember force is minus du by dx. Okay, whereas if I look at a point which is slightly before, that is to the left of this point, this point x's value is a minus delta x. What about the slope here? It's negative.
Negative. Force will be positive.
So that means force is positive. So now let's think about the force at these three different points. Okay. So suppose this is my particle moving along the x-axis. Okay. So this particular point here is x equal to a. So when the particle is over here, or when the body is over here, what about the force on it? It is 0. Okay. But the moment I shift the body now to a point like this, slightly to the right of A, then what is the direction of the force? It's becoming negative. Okay, which you can see here. Whereas if I shift the body towards the left, then the force is becoming positive. So this type of force, this type of combination of force, it is called restorative force. It tries to restore the system. That is, when displaced from the equilibrium point, x equal to a, to x equal to a plus or minus delta x. Okay. A restorative force comes into action. What we mean by restorative force? Force pointing towards mean position, so towards equilibrium position. So this is a property of a stable equilibrium point. That when I displace the body from the equilibrium point in whichever direction, towards the right or towards the left, okay, there should be a tendency for the force to push it back to equilibrium point. So that means there's a restorative force. So that is the property of a stable equilibrium position. Okay. And in terms of potential energy, what this property means is that the potential energy graph should have a local minima at the position of stable equilibrium. Okay, so now likewise we'll see that unstable equilibrium is like kind of the opposite of this. Opposite in the sense that obviously slope is zero at the unstable equilibrium point because net force should be zero. But with respect to that point, if I move the system by a small amount delta x towards the right or towards the left, the force should point in the opposite direction, not towards the point, but in the opposite direction. So that means these are non-restorative forces. They tend to take the system away from the equilibrium point. So the equilibrium point is not stable because even given a slight displacement, the system will move away from the equilibrium point. So we'll see that is a property of the local maxima type of point for the potential energy graph. Okay, so this point is clear. You've written this down, people.
Yes, sir. Done.
Okay. So now you can just see that the unstable equilibrium point, the logic is just the reverse of this. If you look at the graph of the potential energy function at a position where there is local maxima, you'll understand that the forces are such that they are opposite of restorative. They tend to take the system away. Okay. So unstable equilibrium point. So one way to define it is that it is the point of local maxima on the potential energy versus X graph. Now suppose this is the point exactly where the slope is becoming 0. Let's say that's x equal to b. So at x equal to b, slope is equal to 0 because potential energy has local maximum. Okay. So slope is 0 means force is 0. So obviously it's an equilibrium point. But now more importantly, if I shift to this sort of point, you can see that the slope here is negative. That means the force is positive. So looking at the force picture, if I put my body or particle, whatever, at the point x equal to b, the force is 0. But the moment I shift it to the right of, okay, you can see that here the force will become positive. Okay. And similarly for the point towards the left. So these forces you can see now are what we call non-restorative forces. So what that means is that at x equal to b, the net force is 0. But when displaced from x equal to b to x equal to b plus minus delta x, okay, the force push the system away from equilibrium. So this thing is a property of an unstable equilibrium point. Okay. So this whole idea about stable versus unstable equilibrium. Okay. So this is important. Okay. Exactly. Yeah. Ayan, that's true. Okay. You can also relate this with stable and unstable equilibrium can be related with, for example, if we talk about gravitational potential energy. So when a particle is like at the bottom of a valley, okay, for that particular system, at that bottommost point, the gravitational potential energy has a minima. So it's a stable equilibrium point. But if it is at the peak point of a hill, then the gravitational potential energy has a local maxima. So it's an unstable equilibrium point. So at the peak point of a hill, you can see if you displace the particle even slightly, it will tend to run away from the equilibrium point. So that's a simple way to relate this also. So yeah, coming back to this is important because one, of course, direct questions based on this idea can come in your competitive exams, right? And another reason why this is important is because in future, in chapters like electrostatics, gravitation, etc., we will be making use of this concept. Okay, so let's look at a quick example question. So particle of, let's say, 2 kg mass, okay, moves along the x-axis, okay, under the action of a single conservative force only, F, such that its potential energy is given by this. Let's say this is the potential energy function. U is in joules, whereas X is in meters. So first of all, find the particle's acceleration at locate the positions of any stable and unstable equilibrium points. So this is the typical type of application question. So obviously at competitive exam level, this will be MCQ with options. Okay, so suppose you have a question where some potential energy function is given like this, and the options are about, x equal to a certain position is equilibrium point, x equal to a certain position is stable equilibrium point versus unstable equilibrium point. So you have to select the correct options accordingly. So now you can see here that this is a situation where only a single conservative force is acting on the body. Okay. And the potential energy is given by this graph. So it means that the net force is that single conservative force only, and that is minus du by dx. Okay, so this concept will be used over here. And then, of course, use Newton's laws that F is equal to ma. And also, potential energy graphs local maxima and minima point will be our unstable and stable equilibrium points. So these are the two concepts that we will use here to solve the two parts. Okay, so just apply it. It's quite easy here to do the differentiation because simple function. Okay, so let's work this out. So anybody got the first part's answer?
Sir, minus 120 meter per second, sir.
Okay, meters per second square.
Yes, sir.
Okay, let's check it out. Okay, so our force will become minus of the derivative of this term, 10x to the power 4 minus 20x square. So this will become how much? This will become 40x, right? Minus
Sir, 40 cube.
Minus
sir.
40x cube.
minus 40x cube, right?
Oh, yeah, sir.
So we can take also write it like this. So this becomes the formula for force. So now we can see that at x equal to 2 meters, what is the value of force that we are getting? It will be 40 into 2 into 1 minus 4, right? So that is 80 into 3, but minus 3. So minus 240 newtons. Okay. So the acceleration is going to be minus 120
120.
meters
Yes,
per
sir.
second.
Correct, sir. Yeah.
And likewise, at x equal to 10, we can see that. pretty incredible amount of acceleration we are getting. Okay, perhaps the particle should have been much heavier for the question to be a bit more practical. Okay. Anyhow, so this is the first part. Now, what about the local maxima and minima point for the stable and unstable equilibrium? So, given the,
So the du by dx should be 0.
that kind of thing we have to find out. So for this function, we have to
So
find,
just 1 second. So could you just scroll up a little bit to the second question?
yeah,
Just note that down.
local maxima and local minima. Just a moment. Okay. How we'll find this? So we'll use this relation that local maxima condition is that du by dx should be 0 and second derivative should be what? It should be negative. And local minima du by dx should be 0 and second derivative should be positive. So that is the calculus concept that we'll use over here, because that's the only option we have. It's a very complicated function for drawing a graph and all that. So it's not going to be easy to try and directly plot the graph and understand. So we have to use differentiation, application of differentiation. Okay. Okay, so du by dx is differentiation of this function, which we already seen, but earlier we've seen it with a negative sign because we're talking about force. So now we also need second derivative of this. So we need to find out. So second derivative is derivative of this term. Okay, so this is clear.
Yes, sir.
So du by dx is given by this formula. Okay. And second derivative d2u by dx square is now given by this formula. Even this we can factorize, but I'm just leaving it like this. Okay. So now what is the condition for local maxima? That the derivative should be 0 and second derivative should be negative. And the condition for local minima is that second derivative should be positive. So that has to be applied on these two formulae. Okay.
Sir, wait, are these the final answers or like we have to do more?
No, this is still, we have to find the local equilibrium and
Yeah,
I mean,
okay.
you have to
Okay.
find the stable and unstable equilibrium point. Okay, this is just the derivative and second derivative. Now you have to apply this concept which I've shown here. Now, the condition for local maxima and local minima, right? Okay, so have you found the stable and unstable equilibrium points from this? So to find local maxima and minima, first we need to find the points where the slope is 0, right? Du by dx is 0. So first step is these points we call the critical points, no? Where this is happening. Okay. So 40x into 1 minus x square is 0. So that gives us x equal to 0 and x equal to 1 and x equal to minus 1. So there are 3 critical points. Now, which of them are stable or local maxima? Which of them are local minima? So for that, we have the second derivative test. Right. So hope all of you remember this. Okay, so second derivative test, let's look at it. Okay. So d2u by dx square in general we saw is 40 into 3x square minus 1. So therefore we can see at x equal to 0, d2u by dx square is minus 40. No? At x equal to 1, d2u by dx square is plus 80. So it's positive. And at x equal to minus 1 also, it's positive. Okay. So that means x equal to 0 is the local maxima point. And these two have the local minima. So this tells us that, the shape of the graph will be something like this.
Sir, it will not be like plus 80
It will
when
not
it
be
is
like,
minus 1.
Come again, beta, it will not be.
Sir, when x is equal to minus 1, then it will not be plus 80.
It will be plus 80 beta because minus 1 ka square is 1 only, no?
Okay, sir.
But no, it's a x square term, no? It's not 3x minus 1 inside the bracket.
Yes,
It's
sir,
3x
yes,
square
sorry.
minus 1. So, Okay. So therefore, we can now see from this that what is a stable equilibrium position? There are two stable equilibrium positions. Okay. So this system has stable equilibrium at x equal to 1 and x equal to -1, and it has unstable equilibrium at x equal to 0.
Done, sir.
Okay, done now. Okay, so we'll just take a few more minutes to discuss about the basics of power. Okay. Okay, so just like work done has, first a general definition that how to calculate work done by a force. And then once we know the formula of work done by a force, we see that the net work done by all the forces put together on a body, that has a certain relationship, and that is equal to the change in kinetic energy. Like that, power also has a certain relationship with force. Generally denoted with the symbol P. So the word definition of power is it is the rate of work done. Power is the rate of work done with respect to time. Okay, so that means when we are talking about power delivered by a particular force, okay, then that power is defined as rate of work done by that particular force with respect to time. So this power becomes dW by dt, where W is the work done by that particular force. Okay, or we can say that. Okay, so we can also see therefore that power is F dot ds by dt, and since we know that ds by dt is the instantaneous velocity, so now we have, okay, while this is the meaning of the term power in terms of definition, but we also have a formula. It becomes equivalent to F dot V. So power can also be expressed as it is the scalar product of the force and velocity V. Okay. So power is expressed in watts in SI system, where 1 watt is equal to 1 joule per second. dimension of power, as you can see, will become dimension of work done per unit time. So it's like this. So that is about power delivered by a single force. Okay, so now there is also the second thing, the net power delivered by all the forces acting on a body. So this is the net power, is the sum of power delivered by all forces, let's say F1, F2, the n number of forces acting on a given body, let's say of mass m. So this net power will become summation of F dot V. So that we can write as this also. Yeah. So that becomes the net force. So now we know that the net force is equal to mass into acceleration. Okay. And E dot V is equal to This we've seen before, okay? Because A dot V, it is tangential component of acceleration into V. So you can see that net power is also equal to, which is nothing but rate of change of kinetic energy. Because kinetic energy is half mv square. Okay. So the net power delivered to a body is equal to the rate of change of its kinetic energy. So if a combination of forces is acting on a body, okay, then we can calculate the net force and calculate the power delivered by that net force by taking dot product with velocity, and that will be equal to the rate at which its kinetic energy is changing. Okay, so these few questions of H.C. Verma we will discuss in the next lecture then. Okay. I think one or two questions in this are to do with power also. Okay, so you can try those. So that's it for today's session, people. Wish you all the best.
Bye, sir. Thank you, sir.
So could you just give 1 minute, sir? Just
Yeah,
note this down.
note this.
Thank you, sir.
Okay, people.
Sir,
Sir,
one
could
second.
you please share the recording and the notes?
Yes, I will do that.
Thank you so much.
Sir, this got stopped screen sharing. Yeah, okay, thank you. Just 1 second.
Yeah, no problem. Go ahead.
Bye, sir. Thank you.
Okay, people.
Thank you so much, sir. Have a nice day.
Okay, people. Thanks. Okay.